Okay, this should be a fun one. This is Schrodinger's cat, Quantum Mechanics 2. I'm Robert Nemroff at Michigan Tech. This is Physics X, Extraordinary Concepts in Physics, and where I review the coolest concepts in physics. So if you look at the other lectures in these series, you'll find other cool concepts. So Schrodinger's cat is one of the, let's jump to the next slide. Schrodinger's cat is one of the things that everyone's heard of. It's one of the buzz phrases, even in society. You always hear about Schrodinger's cat. So I'm going to try to get into it. This follows naturally on the last quantum mechanics lecture where we went into interpretations of quantum mechanics. So Schrodinger's cat is really all about interpretations of quantum mechanics. It's not about, whether you can save the cat or not. It's about how you think about what happens. In that sense, Schrodinger's cat isn't really that important so far as we can tell for the actual physics. The cat ends up either dead or alive, and how you interpret that isn't all that key. But it's a lot of fun to think about. It gets into sort of the philosophy behind quantum mechanics. And so it's real, and it's also really strange the way quantum mechanics causes people to think about things. One thing is that Schrödinger does use an umlaut here, and so I was not able to get Google Docs to easily give me an umlaut, so please forgive me for not doing that. But let's get to the guts of the matter. You have a cat. You're not a nice person. So you put a cat in a box. Now right off, you're not a nice person for putting a cat in a box. I just have to say that. So even worse, you put in some kind of quantum mechanical device in that box that will quantum mechanically decide based on quantum statistics, not just based on something flipping a big coin which might not be quantum mechanically decided. For instance, the decay of some radioactive element which is here, that would be quantum mechanically decided. Now if the element decays in a certain way, it breaks something open that opens up a gas that kills the cat. So if the radioactive material does not decay, then the cat is alive. And the cat is always in a box right there. So you're sitting outside watching this box, and you're wondering what's happening inside the box. Did that radioactive element decay and kill the cat with the poison, or did it not? The essence of Schrodinger's cat. So you can think about this sort of in two ways. Quantum mechanics comes to two ways. One is just before the box is open. So now it's been a while, so now you're going to open the box and see. Just before the box is open, is the cat dead? And the answers to that are kind of strange. One is either yes or no, but you won't know until the box is opened. So you can say, well, right now I haven't opened the box, cat's dead, I just don't know it. Or cat's alive, I just don't know it. That's one aspect. Another aspect is it's kind of made fun of. This is the Copenhagen, well, we'll get into this. Both yes and no until the box is open. So the box is closed, the cat's in the box. Can you consider that the cat is both dead and alive until the box is open? Then, after the box is open, then the cat's either dead or alive. This first arose in 1935, this question. So it's less than 100 years old. It was described in letters exchanged between Schrödinger and Albert Einstein. So Einstein in particular was very fond of writing off letters about things and trying to solve things in his mind. And when he came up with something, he would write letters. And he knew all of the major physicists at the time. And he was constantly exchanging letters with many of them. Einstein, as you know, wasn't happy with quantum mechanics in general. He kept trying to shoot down the uncertainty principle, thinking that, no, it's just not right. In particular, Einstein wasn't also happy with the Copenhagen interpretation of quantum mechanics, which was reviewed in a previous quantum mechanics lecture, where there's something called wave function collapse. Einstein, in his letter to Schrödinger, considered a powder keg that he considered to be paradoxically both exploded and unexploded in the Copenhagen interpretation until you find out. He said that's absurd. Schrödinger agreed, and he replied in his letter back to Einstein with the famous cat paradox. Schrödinger did not actually expect that this experiment, or a non-killing version of this experiment, would ever be done. Einstein, I guess, had considered, and Schrödinger in his reply, considered it a reduction to absurdity. Isn't it so absurd that according to the Copenhagen interpretation, the cat is both dead and alive, that it just can't be true? And so since the Copenhagen was the usual interpretation that was given to quantum mechanics, therefore, quantum mechanics is an incomplete theory, and although it might seem to predict the results of experiments, we should dig deeper and know better, hopefully soon. So the Copenhagen interpretation, as I said, said clearly that the cat is strangely both dead and alive. It's sometimes written in this, there's an alive state plus a dead state. And both of them have positive numbers there. So according to the mathematics, which seems to work, strangely enough, it's both dead and alive. Now, when the box is opened, then you find out, and then it's like dotting some state, open state, to the other ones, and you find out that the cat can't. Once the box is open, the cat can't both be dead and alive. Everybody agrees with that. It turns out to be one of them. Now, people say, well, I don't believe this, because if you kind of, peek in the box, or you listen to the box or something, then how can that be? So what's really here, the box could be made of anything, really, but one of the important things of the box in the Schrodinger's cat thing is that you can't do anything determinative to the box to determine whether the cat is dead or alive before. So you don't actually have to open the box. You can X-ray the box. You can do a quick peek in it. You can listen to the box very clearly and hear the gas being expelled. That's all equivalent to opening the box. Okay. A contrasting interpretation comes about either of two ways. The many worlds interpretation, both which include decoherence. The many worlds interpretation says that separate universes house the dead and alive cats. So in one universe, the cat died. In another universe, the cat's alive. And you get to find out which it was only when you open the box. The two universes where the cat was alive and the cat was dead, they don't interact. So essentially, everything's already decided in the many worlds interpretation before you open the box. Then, you're opening the box is not such a dramatic event. You just get to see what has already been decided. In the ensemble interpretation, individual cats are either dead or alive, but not both, and you can't know which until the box is open. So the only way you can build up statistics is to knock off many cats with doing the experiment on many cat systems. So they would say that either yes or no. Mathematically, I'll say, it doesn't really matter. The standard math of quantum mechanics, the Schrödinger equation, Dirac equation, if you want to go relativistic, they say pretty unambiguously what the math says. So the probability when you open the box that if the cat is 50% dead or alive in both interpretations, you're going to have 50% time you're going to have a live cat, 50% dead cat. It's really a question of philosophy at this point. However, some people disagree with that, and we will see in the next lecture, Quantum Mechanics 3, that people sometimes try to go against particularly the Copenhagen interpretation, because that's the most famous interpretation that most physicists would believe. But it doesn't really matter. Many worlds, ensemble, and Copenhagen all use the same math. We will find out that the hidden variable doesn't really use the same math, and that was one of Bell's great understandings, that the hidden variable theory will take you on different courses. People still try, though, to say that Copenhagen will give you a different interpretation, different math than others. But so far as I know, no experiment has ever been done that has shown a real mathematical difference in statistics between many worlds, ensemble, and Copenhagen. So I have some thoughts on this. who cares what I think, but here we go. I try to bring you up to my level of incompetence, which is certainly no one fully understands quantum mechanics, so I misunderstand it at some level. Perhaps it'd be interesting to see at what level I misunderstand it. So let's say with popular TV shows these days that a crime scene investigation looks at the dead cat. So you open the cat box and the cat was dead. It's not so interesting if the cat's alive. That could happen. So you might have your CSI team find out how warm the cat was. They might be able to tell from that and from other information inside the box how long the cat was dead. And then you can see, aha, since I now know the cat was dead fully an hour before I opened the box, then that negates the Copenhagen interpretation. Because the Copenhagen interpretation, some might say, would only say the cat died when you opened the box. But that's not really what the Copenhagen interpretation is. It's fully consistent that the cat could have been dead for an hour before you opened the box. But you only found out about it. The wave function of your knowledge, sort of, only came about when you opened the box. So even if you had a CSI team look at the box, look at the dead cat, and figured out it died sometime earlier, that doesn't negate the Copenhagen interpretation so far as I can understand. Next, here's where my real understanding drops off the edge. I don't know what happens if you only gain some incomplete information. Let's say you find out that one side of the box is slightly warmer than the other side. Does that mean the cat was sleeping on that side recently? What's the temperature difference? So you're given incomplete information about what's in the box. What happens then? I don't know. So that's my understanding of Schrödinger's cat, and partly quantum mechanics stops at that point. You could try to get into sophisticated mathematics. I don't know if that would help. Wigner's friend. So this gets into whether consciousness is involved. So Wigner, a famous physicist, his friend, he didn't actually perform. No one's actually killed a cat this way. But let's say that his friend is the one who performed the Schrodinger's cat experiment. Wigner was away. He was out shopping. When he returned, his friend then tells him the result of the experiment. So what about for Wigner? When did the cat stop being a state of both dead and alive, according to the Copenhagen interpretation? Was it when Wigner's friend opened the cat box, or was it when Wigner's friend told Wigner the result of the experiment? So this is somewhat debated. It probably wouldn't change. The mathematics wouldn't change. But it's debated as to whether how much consciousness plays in this result. What determines wave function collapse at all? Okay, quantum suicide machine, I got to quickly here. So let's say you're in a box, and you yourself are in a closed box, and a quantum mechanic device could kill you 50% of the time. After many of these quantum events where it could have killed you 50% of the time, will the experimenter survive? Either no, the experimenter luck will run out, or yes, experimenter cannot be killed by such a device. Got to go quickly here. So the Copenhagen interpretation would say no. The chance of death will eventually become so great because of the accumulation of 50% that you'll die. The many worlds interpretation says if you're the experimenter, you're only reporting on this if you're alive. So you might have almost died 50 times yesterday, but since you're here today, they've all come out positive. So the many worlds interpretation will say yes. So this doesn't give a testable result that we can really tell the difference as to which is the real interpretation of quantum mechanics. Does this require a conscious experimenter? Again, something that's debated. And with that, I will, at the end, for one time, say keep Schrödinger away from your cat. Oh, one more. I think I'll do this next time. So I'll conclude with the previous one. Please keep Schrödinger away from your cat, and I'll move this into the next lecture. Okay, this should be a fun one. This is Schrodinger's cat, Quantum Mechanics 2. I'm Robert Nemroff at Michigan Tech. This is Physics X, Extraordinary Concepts in Physics, and where I review the coolest concepts in physics. So if you look at the other lectures in these series, you'll find other cool concepts. So Schrodinger's cat is one of the Let's jump to the next slide. Schrodinger's cat is one of, and so it's real, and it's also really strange the way quantum mechanics causes people to think about things. One thing is that Schrödinger does use an umlaut here, and so I was not able to get Google Docs to easily give me an umlaut, so please forgive me for not doing that. But let's get, it's about how you think about what happens. In that sense, Schrödinger's cat isn't really that important so far as we can tell for the actual physics. The cat ends up either dead or alive, and how you interpret that isn't all that key. But it's a lot of fun to think about. It gets into sort of the philosophy behind quantum mechanics, the things that everyone's heard of. It's one of the buzz phrases, even in society. You always hear about Schrodinger's cat. So I'm going to try to get into it. This follows naturally on the last quantum mechanics lecture where we went into interpretations of quantum mechanics. So Schrodinger's cat is really all about interpretations of quantum mechanics. It's not about, whether you can save the cat or not.